Okay, great. Yeah, we've had quite a lot of like really good, really hardcore talks. I think I'm going to make things a little bit easier. Two definitions, one theorem, one example, and a table spread over 15 slides because I can't stop talking. Uh, so, hopefully at some point in your life, you all heard about reducibility, probably in an undergraduate lecture called computability or something. The idea is that you want to, in a relative as opposed to like an absolute manner, decide what computational problems are harder than others. And what you get like quite a good theory out of this. You hear about classes like P and NP, but probably what isn't something that's came to your mind before is that you can actually order non-computable logical principles in this way and study non-computability computably, so to speak. Um, so the kind of reducibility theory I want to talk about today is called Weierach reducibility. The most important things you need to know are this picture and that we're working in a setting called type 2 computability. So you have Turing machines. Yeah, I know. They've taken an infinite sequence of numbers and spit out an infinite sequence of numbers. They're transformers. And when you want to have an oracle that you can call as kind of like a subroutine, that's a little bit problematic because you need to give it an infinite input to get your answer back out. But if you only make a single oracle call, then things kind of work out kind of nicely because every solution kind of looks something like the thing on the left. You have some pre-computation, this file on the top, an oracle call, and some computation going in a backwards direction. And then you can just sort of run everything as like asynchronously talking to one another. And everything works out okay. So this picture is the important thing, but I promised you two definitions. Here's the first one. If you understood the picture, I've just mathematized it, along with some convenient lies to make things go a bit smoother. So a Weierach problem is a relation on sequences of natural numbers, and you can reduce one problem to another when you have a map between the domains. I've written them out as families where the domain is the indexing set, and for every element in your domain, you have a non-empty amount of solutions. So you have a map going one direction from domains to domains, and a family of maps going in the opposite direction from solutions to solutions. And we'll see if I can talk about strongly reducible at some point, but that's basically you ignore your initial argument and only work with the oracle call directly. So to test our understanding and to talk about some non-computable stuff, here are two examples of non-computable problems. So the least principal omniscience is just decide whether or not the infinite binary sequence is the zero sequence. And Koenig's lemma is if I give you a finitely branching infinite tree, find me the infinite path in it. And this is an equivalent statement. The weasel words here being given by enumeration. If you know, you know. If you don't worry about it. And so I don't know about you, but I definitely think that Koenig's lemma sounds like a stronger statement than LPO. And because trees are more complicated than sequences. And that is in fact the case. We can reduce LPO to Koenig's lemma. We cannot reduce Koenig's lemma to LPO. And I'm going to show you how to do one direction. For the other direction, you'll have to look up the slides or find me after the talk. So proof by animation, a very common proof technique. So I start with a infinite binary sequence at the top, and I'm going to try and create a tree to give to my oracle. And so every time I see a zero, I'm going to add something along the leftmost branch. So attach something to the left of the root, attach something to the left of that, attach something to the left of that. And if I only ever see zeros, I'm going to end up with this tremendously degenerate binary tree that's just a big sequence down the left. Whereas if I ever see a one, I stop and start again from the beginning and go down the right instead. And the important thing about this procedure is that, one, it gives you an infinite binary tree, and two, there's a unique infinite path in this one. So when I say almighty oracle, give me the infinite path in this tree, well, from that, depending on whether or not the first thing was a zero or a one, I can then answer the initial question about whether or not the sequence had a zero or one in it. So I feel comfortable saying that KL is at least as strong as LPO now. To prove that they're not the same degree, well, see me afterwards. So the Weihrauch degrees give you a pretty complicated ordering. This is not a quote from Pradic, but it may as well be. And we're not really going to need any of the structure. I just want to impress you. But they do have a lot of algebraic structure, which is kind of more interesting to me. So when you look at the equivalence classes in this ordering, you don't just get a poset, you get a lattice. And I'm defining these in a bit of hand-wavy way. But to take the join, I either ask a P question or a Q question, and I get the appropriate answer back. To get the meet, I say, here's a P question, here's a Q question, give me an answer back. Parallel product, give me both answers back. And the really cool one is composition, which lets you cheat and ask multiple questions. And the way you encode this is just, instead of ask one question and then have a strategy for asking questions and get two answers back, or as many, or finitely many. So that is basically all you need to know about Weihrauch degrees. Then we're going to get to containers in a second. So this definition that I put up before is already pretty general, except for the only problems are like this stuff in red. Some of it is just you could work in a different category. You could work with just normal Turing computability with, for example. And then the only other kind of annoyance is all of this family stuff. So hopefully everyone has seen the trick for how to work with families in a category before. They're the same thing as maps. To go one direction, take preimges. The other direction, take the disjoint union, and there's a projection map out. And the nice thing is, if you're in a category with pullbacks, then re-indexing your families is just taking pullbacks. So everything I will say from now on is implicitly in categories with pullbacks. If you've never done this exercise, it'll take you about 10 minutes. It's really easy. So I wave my white magic wand, and now suddenly the definition of Weihrauch reducibility becomes this. The weird bit is, of course, your inputs are in the codomain, not the domain. And I guess we haven't seen a formal definition of containers. I was kind of hoping Andre would. But with the sufficient categorical rewriting, this is the definition of a container, and this is the definition of container morphism. So that was a nice thing to learn. Because, well, first of all, it's really good to see the same thing over and over again. Containers have been invented a dozen times. I don't know. Jules has a nice blog post about it. I'm not going to cover all of these, except to point out that this topological complexity one, this isn't even the first time that containers were invented in the context of computability theory. Hirsch beat us to it by 30-something years. Yeah, so I promised you a theorem. The theorem is kind of at the bottom. So if we work in a sufficiently good category for doing computable analysis, the category of partition modus sets over a cleanly second model, and we look at what I've called answerable containers, if there's an actual name that containers people have for this notion, we'd prefer to use it. But the moral of the story is questions should have answers. Otherwise, don't put it in your domain. And so, yeah, this is kind of like the foundation of like what I've been doing for the past couple of months is this theorem right here. I think I'm talking too fast, haven't I? So yeah. So as we saw in Andre's talk, this category is just overflowing with monoid structures. And also some cool new cool operators, like you can define containers recursively. There's this notion of a zipper. And for most of the past 6 to 8 months or so, I've been trying to figure out how all of this stuff matches up with match up what the people on the Weihrauch side know, what the people on the container side know, and seeing what's the same and what's different. And here is my table. I like a good table. So in this framework, we're able to handle the Weihrauch degrees, also Andre Bauer's extended Weihrauch degrees. You just work over a different category. Thanks to people at Strathclyde, this strong reducibility notion is something we can do with things called dependent adapters. A bunch of the algebraic structure just lines up one-to-one, products become mates, co-products, joins, etc. Composition of Weihrauch degrees and composition of containers has a star next to it because, well, this category that we had before at the bottom here doesn't have exponentials in it. It has a fair amount of structure. It's got enough projectives, so we can conjure up a weak exponential, but weak exponentials aren't enough to get an actual functor here. So tick star, try again. And there's a whole bunch of stuff that I could talk about. For example, there's this diamond operator, which is ask finitely many questions, but as many as you like. We contend this is the same thing as the free monad on P. The derivatives get an X because we figured out last week that they don't work in the Weihrauch degrees because derivatives aren't functorial. Yeah, I'd be happy to answer any questions you have or to just explore this analogy further. Thank you.